Hi guys, we're back to talk more about geology, and this time we're going to talk about intrusive igneous rocks. So let me get the screen up here for us. Okay, so igneous rocks, we should know by now, are rocks that form when we have some sort of molten geologic material, so either a magma underground or a lava on the surface. And an igneous rock is when that molten material cools down and freezes. And that doesn't necessarily mean it has to get super cold, like the temperature that water needs to freeze. Rock has a different freezing point than water. So it's going to be still what would seem pretty hot to us when this process happens, but it's still called freezing or the solidification process. And once it does that, then it becomes a rock. So rocks that form below ground from magma are intrusive igneous rocks. They form in the interior or the inside of the earth, as opposed to extrusive igneous rocks, which form on the earth's surface or on the exterior. And intrusive rocks, because they cool down and solidify on the inside of the earth, experience that transformation from a liquid to a solid relatively slowly compared to extrusive rocks. And that's because all the other hot rock around them is a pretty good insulator. And so they're not losing heat very quickly. And so this slow cooling, which I'm noticing right here, this is not how you spell slow, I'll change that later. But the slow cooling process means that larger mineral crystals have an opportunity to form. And so in general, one of the ways that we can recognize intrusive igneous rocks is usually we can see the different mineral crystals with our naked eye. We don't need a high-powered microscope to recognize that there's different kinds of minerals within the rock. So over here we have granite, and then over here we have, this is probably like a gabbro, a more mafic igneous rock. But in both cases, you don't need a microscope. You can probably just pick out with your naked eye that there's some darker and lighter mineral crystals that represent different kinds of minerals. And we can see those different little crystals, little minerals, with our naked eye. Okay, so how do they form? Well, they form from magma. We know that magma, which is a liquid, is less dense and therefore more buoyant compared to solid rock, which is a more dense form of this kind of material. And so therefore, once magma forms underneath the earth, it starts to rise up. It's not being pulled by the force of gravity quite as effectively down towards the earth's core as solid materials nearby. So it will kind of rise up, it will buoyantly bubble up through cracks in the rock. And you can kind of imagine this as like, if you had your toes in the mud, and then the mud that's underneath that's liquid is less heavy or less dense, I should say, relative to your toes. And so your toes will start to sink down, and then the mud will start to kind of squirt up through your the cracks between your toes. So this is the same kind of process that happens with the solid material underneath the earth and then the magma that's kind of moving upwards through cracks that are present. And when it gets to a cooler environment near the surface, it will eventually cool down enough, drop its temperature enough that it will start to freeze and solidify. And so this might happen when it just kind of sits up near the Earth's surface for a period of time, just in a cooler environment, or as it just loses heat to other rocks around it that are cooler, that are sapping energy away from it. Of course, sometimes the magma comes all the way up and out of the earth and freezes on the earth's surface, but in that case, the rocks that would form, again, would be extrusive as opposed to intrusive rocks. So when this magma has an opportunity to adequately cool underneath the earth, then it's going to form an intrusive igneous rock. Okay, so we call these rocks intrusions because they kind of intrude into older rock that existed around them, and we have a term called country rock that we use to refer to the older different like strata, and that country rock can be all kinds of different rocks. It could be sedimentary rock, metamorphic rock, other igneous rock, and you can kind of see from this diagram here, there is a pluton, which is kind of a large mass of magma that has frozen underground. It's usually on the scale of like a big magma chamber that would have sat under an old volcano. And when that all cools down and forms a big area of igneous rock, we would call that an igneous intrusion. But that particular type of large size igneous intrusion is called a pluton. And then within a pluton, we might have little pieces of country rock that broke off from the rock around. Maybe part of the country rock melted a little bit, and then part of it kind of contaminated or assimilated into the magma. But some of the pieces of country rock maybe didn't completely melt. And so then we might have these little pieces of kind of foreign rock inside the pluton or inside the igneous intrusion, and those are called xenoliths. So xeno means foreign, lith means rock, so that's a foreign rock. And so up on the top right, you can see sometimes when you look at like big granite domes and stuff, you'll see these little fragments of kind of a different, usually colored rock that's inside within the granite, and that would represent one of these xenoliths. And then when we talk about metamorphic rocks later, we'll talk a little bit about this zone where there's extra heating of the country rock along the edge of the magma intrusion. And that can actually change some of the country rock and create some metamorphic rocks there. So anyway, this is what it might conceptually look like underneath the ground. And so here's some real world pictures. Here is a mountain range down in South America in Chile. And you can see on top, there is some shale, some country rock. Shale is a type of kind of sedimentary borderline metamorphic rock up here. And then below it, you can see this lighter colored rock, and this is granite. And from this distance, you can't see the little kind of salt and pepper flakes that characterize granite, but if we were up closer, we would be able to see it. And so this granite represents a big magma intrusion that came into this shale country rock, and then it froze inside the country rock. And then over many hundreds of thousands of years, the overlying landscape eroded away, and even some of the pluton itself has started to erode away. And so now we have this intrusive igneous rock that is exposed at the surface. And there are some places in the Eastern Sierra where you can see this kind of thing as well. And then speaking of the Sierra Nevada mountain range is essentially a mountain range of lots of different old plutons. Many plutons all together within a region is sometimes called a batholith. I don't have that word written on here, but B-A-T-H-O-L-I-T-H. And so famous granitic plutons in the Sierra Nevada range include things like Half Dome in Yosemite, or North Dome in Yosemite, or El Cap in Yosemite, or Grizzly Dome isn't necessarily a famous granitic pluton, but that's in Plumas County. That's what the tunnel kind of goes through in Highway 70. And then there's, of course, other granite in places like Tahoe and all up and down the Sierra Nevada. And so the I do have batholith on here. The Sierra Nevada batholith is a big mountain range that today is exposed at the surface, but formed around 100 million years ago, but not all at the same time. So in the range of about 145 to 80 million years ago, there was some subduction that was going on between a plate that's almost completely disappeared called the Farallon plate that was subducting underneath the North American plate. And as it went, it was carrying down volatiles, which we know is one of the things that can create magma. And then that magma was bubbling up to the surface, and there was a series of many magma chambers that were underground, and they fueled a series of ancient volcanoes that was called the Nevadan range, that was kind of above the present day Sierra Nevada, that was erupting in the range of 100 million years ago. And over the last 100 million years ago, that surface material has all eroded away. Much of it's in the Pacific Ocean, some of it's filling in the Central Valley of California. And today we are walking around on the surface of these old plutons that form this giant batholith of the many kind of couple hundred mile long Sierra Nevada mountain range. So the range of light refers to the fact that all this granite that kind of forms the surface of these plutons is a relatively felsic rock. It has lots of quartz in it, lots of feldspar in it that's relatively light in color, and so it's a very light colored rock. Anyway, that is another example of an intrusive rock. And then here is a picture of the subduction that was going on. So from the bird's eye view, there was this plate that before was between the Pacific plate, which is now in contact with the American plate and the North American plate. The Farallon plate was subducting underneath North America. Up on the top, we have a cross-sectional diagram reminding us what a subduction zone looks like. Hopefully you're familiar with this by this point. Forming magma because of the introduction of volatiles, creating volcanoes, and then these plutons underneath create the batholiths that we see today. So here is kind of the modern area of the Sierra Nevada, and we live right up at the top of it here in Plumas County. We're at the very, very edge of the Sierra Nevada. Some of the very farthest north granite that's part of the Sierra Nevada range is in Plumas County, in places like Grizzly Dome in this Highway 70 Canyon, and in places like Antelope Lake. There's some granite there. Okay, so we can have these big size magma intrusions that form plutons. We can also have kind of narrower fingers of magma that freeze underneath the ground. And those are usually referred to as dikes or sills. So sills are what we would call concordant structures in geology, which means that they run in the same direction to the pre-existing layers. So they kind of, the magma would come up and then it would kind of fill in a weak layer in between two geologic strata, or that's another word for layers in geology. So you can see that over here. And then a dike is something that is discordant, cuts across the typical pattern of the layers. So those are just kind of like smaller fingers of magma that cooled underground. And then this is called the snake dike on Half Dome, and it's a climbing feature. A lot of rock climbing features are these dikes, which give people something to hold on to in rock climbing. So it's not uncommon if you're into rock climbing that you might have climbed on one of these before. And often these intrusive igneous rocks are pretty hard and pretty weather resistant. They don't break down as quickly as other rocks, and they also, of course, are going to be usually young or always younger than the rock that they intrude into. And so they often don't break down as quickly, and so therefore they might be kind of sticking out as other surface layers erode away. That is going to be this finger that is kind of resistant to weathering, but still protruding out beyond the other layers when this erosion happens and they get exposed to the surface. Okay, another feature that you might see is a volcanic neck. So over here on the top right, we can see the magma chamber down here would cool down to form a large size pluton that might be on the scale of like many miles wide, or like a mile wide, half a mile wide, depends on the size of the magma chamber. And then we have these small little concordant and discordant fingers, dikes and sills. And then we know that many magma chambers have magma that comes up to the surface that feeds a volcanic feature on top. And so those are called volcanic necks. The magma comes up through the neck of the volcano. And when the volcano starts to cool down and the magma starts to cool down, we have some magma that might freeze inside the neck of the volcano. And just like with the dikes I talked about on the last page, that feature is often going to be more resistant just because of generally its makeup, but also because it's younger than the kind of country rock in this case, which is other volcanic, extrusive volcanic rock that formed from the volcano that's nearby. And so it's usually gonna weather or erode, break down more slowly than the other rock around it. So as the volcano erodes away, often we'll have these big volcanic necks that kind of persist and stick up on the landscape away, up above the other landscape as all the volcanic features erode away around them. So this is kind of a famous geologic feature that's called Shiprock, that's in New Mexico, and there's this big volcanic neck, and then there are this kind of series of dikes around the volcanic neck that are sticking up on the landscape around them. Devil's Tower in Wyoming, which you've likely seen a picture of, or even if you haven't seen in person, is another example of a volcanic neck. And we have some of these in the Sierra Nevada as well, even in eastern Plumas County. Here is in Sonora Pass, here's an old volcanic neck. So these are things that you might have noticed around in the past. Okay, so how is space for an intrusion created? Well, in the case of dikes and sills, these smaller fingers that are formed when magma is kind of intruding into the landscape, they're usually created where there's already kind of an existing crack within the rock. So when the crust is stretched in general, and it's already kind of a hardened, cooled down rock, it will crack because it's not really flexible. So this might have happened in the past because of rifting zones or old rifting zones that kind of started and then died off for whatever reason. So they might have just left behind these existing cracks within the rock. Other kinds of tectonic processes, transform boundaries, and other kinds of pushing and pulling on rocks can of course crack these relatively rigid features as well. And so once we have cracks on the landscape, when magma is around, magma is going to kind of preferentially flow into these pre-existing cracks. And these may be, again, discordant, cutting across layers, or they might be kind of in between layers. So the rock might not be as well fused together between two layers of different material or different aged material. And so magma might be able to kind of flow in between those to create a sill. In the case of plutons, which we know formed from bigger scale magma chambers, which are much bigger than what an existing crack would have looked like on the landscape. We know there's not huge holes underneath the earth that are just waiting for magma to fill into. So the process of the forming of space to create a magma chamber is a little bit less well understood, but the understanding is it's probably a combination between some existing crack that probably was there in the first place that magma started to flow into, and then as the magma flowed into that, it was probably pushing the country rock out of the way. So the force from the magma was literally just opening up some space for itself by pushing outwards on the rock. And then in addition, it was also probably melting and assimilating some of the country rock into itself. So it's kind of melting a hole for itself, but then also pushing outwards on the country rock to create this space. And we know that at least some assimilation is happening because we talked about the presence of these little xenoliths, these little foreign pieces of country rock that are found within these magma intrusions. Okay, so as we mentioned before, at the beginning of this video, one of the really recognizable things about intrusive igneous rocks is the fact that they usually have these large sized mineral crystals that are big enough that we can see them with our naked eye. And we mentioned that this happens because there's a slow or relatively slow cooling process. And so it gives the mineral crystals that are forming a pretty long time to be able to cool. So in general, the rate at which cooling happens in igneous rocks in general has a big impact on what the rock is ultimately going to look like. When really fast energy loss or heat loss happens, that is going to cool down the melt really quickly, and that's going to result in really small crystals, and that's what we see generally in extrusive rocks. On the bottom right over here, I have a picture of what are called pillow basalts. So this is lava that extrudes out into the bottom of the ocean, which is very cold, and it causes the lava to cool very, very quickly. So first of all, it forms very, very small mineral crystals that we can't see with our naked eye. And then in addition, as the lava comes out, it doesn't even flow very far from the vent of the volcano, but instead forms these little blobs that are the size of like big pillows, or small pillows, depending on exactly what's going on. But they form these round blobs that are called pillow basalts. And that, of course, is really different than things like granite that we've pictured before a couple times already, that has this distinctive kind of salt and pepper look, where we can pick out the individual minerals and sometimes even recognize what mineral is which just with our naked eye, because they've formed slowly enough to have a pretty big size. Okay, the temperature of the surrounding environment is going to have a big impact on how fast the rock cools down. So in general, when there's a bigger temperature difference between the surroundings and the magma or lava itself, that is going to determine how fast it cools down. When the surrounding environment is pretty similar to the temperature of the melt, then there's not going to be rapid heat loss, and so it's going to cool down pretty slowly, and that's what happens inside the earth in intrusive rocks. So the magma is hot, but the inside of the earth at the depth where the magma exists is also hot. So that would be like cooling down inside the oven. The oven is hot, and so like your cookies aren't going to cool down very fast if you leave them in the oven, because there's not going to be a rapid heat transfer. Whereas if you take the magma out and then you put it in the bottom of the ocean, or you put it out in the air, that environment is a lot colder than the magma. It might be like 1,000 degrees Celsius difference. And so in that case, you're going to cool down that material very quickly by having a very rapid energy move from a higher temperature material, the melt, to the lower temperature environment. So that would be like taking your cookies out of the oven and putting them in the freezer. They're going to cool down a lot faster in the freezer than they would if you leave them in the oven. And again, that contributes to the same determination of how big the crystals end up getting based on how long they have to form during the cooling process. So not only is it a matter of the differences in temperature, but it's also the differences in material. In general, rock is just a better insulator. Heat moves more slowly through rock compared to water and air, which are not as good at insulating you. So that's another reason why the slow cooling process happens underneath the earth, where it's 1, hot and 2, made of rock. So those are both reasons that are going to slow down the cooling process. Okay, another thing that affects the rate at which the melt cools down, which then affects the size of the crystals that we get in the rock, is the surface area to volume ratio. So how much kind of exterior material, outside material, is the melt in contact with relative to how much melt you have. So if there's a lot of contact places between the melt and the surrounding environment, then there's going to be a lot more area over which that energy transfer can happen. So like in a dike or a sill environment, there's just a narrow finger of melt that's coming in contact with lots and lots of country rock. Whereas in a magma chamber, there's a lot of magma that's not actually in contact with the exterior country rock at all. A lot of it's just inside, only touching other hot magma. So in the case of the sill and dike, there's a much higher surface area to volume ratio. And in the case of the magma chamber, there's a much lower surface area to volume ratio. There's not a lot of surface area compared to how much volume of magma there is. So the sills and dikes cool down much faster, and they tend to then have finer grains, meaning smaller sized crystals. So finer grain is another way of saying smaller sized mineral crystals that won't be as easy to see or easy to distinguish. Whereas plutons and then bigger batholiths made up of many plutons usually are going to therefore cool down more slowly. So they're likely to have larger grain size or larger mineral crystals. Okay. So then a final thing that might affect the rate of cooling is the presence of groundwater. Water in general is really good at absorbing and stealing energy. If you've ever been swimming around in the water, you might have experienced this yourself. But when there's groundwater passing in the area of magma or in the area of the rock, it's going to be good at absorbing and stealing heat. So that's going to increase the rate at which the magma cools down. Okay, I think this is the last part of this video, and this one's getting a little long, sorry. So the texture of the rock has to do with the grain size of the rock. And so the rate of cooling, we've already mentioned several times now, has a big impact on how big the different crystals get. And so that is something that would be described as the texture of the rock. And in general, the faster you cool, hopefully we already understand, the smaller the mineral crystals are going to be. And sometimes a melt will cool so fast that the individual atoms don't even have time to arrange themselves into the true mineral structure. So remember, when we learned what a mineral is, one of the things that we said about a mineral is that it has this very precise way that the different atoms need to be aligned with each other to have the characteristics of the mineral. So sometimes melts cool so quickly that they form a solid before they really get their ducks in a row. They get into this mineral crystal structure, this crystal lattice structure of a particular mineral. And when that happens, we get a glass as opposed to a true mineral. And so obsidian is an example of a volcanic glass where a melt cooled so quickly that it didn't actually form any of these true minerals at all. But then beyond that, we can have minerals that form more quickly, that are smaller sized, and minerals that form more slowly, that are bigger sized. And we have different terms to describe this. So aphanitic crystals are too small to see. So many times you might pick up a rock and it just kind of like looks gray to you or looks brown, and you can't really see the individual grains. And that's not because it doesn't have mineral crystals in it. That's just because they're so small that you can't see them. On the other end of the spectrum, a lot of these intrusive igneous rocks are what we call phaneritic, which means that they have large visible crystals. And in this case, this particular intrusive igneous rock has mineral crystals that vary pretty distinctly in size. And so this is called having a fragmental texture, or it's called porphyry, or a rock that's porphyritic. And that is a rock that has both larger size and smaller sized crystals. So the smaller sized crystals in the background are referred to as the ground mass. And then the larger sized crystals are referred to as phenocrysts. So I have one example down in the science building for you guys to look at that has a view of a rock that has these phenocrysts in it, or this is called a porphyritic rock or porphyry. And what this tells us about the rock is that it cooled down in 2 stages. So there was some sort of cooling that happened for a period of time where maybe the magma rose up kind of close to the, or I don't know, to a higher position within the landscape, and it started to cool. And so certain crystals started to form, and they had a longer period of time to form. And so they got to be quite a bit bigger than the other crystals. And then there was a later stage of cooling where the rest of the materials cooled much more quickly, and they formed then, therefore, smaller crystals, which didn't have as much time to grow to as large of a size. So when we see this, we know that this represents that there was 2 distinct phases of cooling in the process of forming this intrusive igneous rock. Okay, I think that's our stopping point for this video.